Allison. Hello, everybody. Let me say that again. Hello, everybody. Happy Friday. It is my pleasure. We'll make announcements at the end. Can we, please? Yeah, my pleasure to introduce Allison Dorsey. All of you know her. She's going to tell us about Radon and the Yorktown Formation. This is really cool stuff. So let's welcome Allison.
Thanks, Linda. So yes, today I'm going to be talking about the stratigraphic distribution and source of radon in the Yorktown Formation. And before we get into the actual geology of it all, I thought I would start off by talking about how I got into radon as an interest for my thesis in the first place. So it all began about this time last year. I saw an email from the Geo listserv and it said, internship, Delaware Geological Survey, and I clicked on it and I saw that it was working with well data and sediment cores. And if you know me, you know I love a sediment core, and so this really piqued my interest and I applied and I received the position. So that was really exciting. But one component of this internship was that I needed to tie it in with my senior thesis. So working with sediment cores, I had a lot of routes I could have taken, but I decided I had an internship in working with Jim in the Gamma Lab. And so that's how I got here today. And before I started my research this summer, I had a few goals that I wanted to accomplish. So first, I wanted to learn about the coring process. Last year, I got to take a lake sediment core with Nick Velasio, but that was very different from what I was going to be doing this summer. So the coring process for the lake core took about 2 hours, and it was a little gravity core that you just drop into the lake. Very easy, about 2 people can do it. The coring process for DGS was completely different. It's a huge core rig, gigantic. I have no idea how much it weighs. And we're coring about 600 feet into the earth. So very different, but I was super excited to learn about that. I also wanted to learn how to accurately describe a sediment core. So this is really important for scientists in the future. I need to be able to describe this sediment core accurately and uniformly so that 20 years from now, they can look back on my descriptions and see exactly what I was seeing. I also wanted to describe and sample 4 specific cores to my study site for my senior thesis, and also run these samples on gamma detectors, which would tell us if things were radioactive and had radon in them. I thought I would start off talking about radon with this old newspaper clipping. It's from the 1980s, and a man named Stanley, who lived in Philadelphia, worked at a power plant. And one day, as he was walking through the radiation detectors, the alarms were set off. And he was walking into work and he set them off. And so investigators were looking into how he was setting off this alarm for weeks on end. And they found out that it was actually his home that was causing so much radiation that he was breathing into his lungs. And there's one section of this clipping says breathing the air in his home would be like smoking 135 packs of cigarettes a day, which I did a little math, and that's about 2,700 cigarettes a day, meaning you would have to smoke 1 to 2 cigarettes every minute to be exposed to that much radiation that he had. So this is a very new threat compared to other environmental threats. It's very understudied and only was really discovered in the 1980s. And just a little bit more about uranium as a parent isotope. So uranium decays into radium-226, which later decays into radon-222. These are all radioactive materials, except radon is a gas, which is why it's so dangerous to us, because it can creep into cracks in a basement, and then you're exposed to it and you can breathe it in. And this is really dangerous because radon kills more people every year than drunk driving. It's about double the amount. It's about 20,000 in the US per year. So it's a very dangerous gas. And this map by Gunderson and Schumann, made in 1996, shows the generalized geologic radon potential in the United States. So areas that are shaded in a dark black color indicate high radon potential, where areas with no shading indicate low radon potential. You'll notice that where we are on the map is just characterized as having low radon potential, but after about 20 years of radon research with the William & Mary Gamma Lab. We've collected data on different homes in the area, and we've received data that show moderate to high levels of radon. So while this map was a great start to understanding radon and where it can be found, it's largely inaccurate, especially for us in Williamsburg. More about the Yorktown Formation. This has been thought to be the cause of radon in the coastal plain. So the Yorktown is just described as a shelly sandy clay or a shelly clayey sand that stretches from Virginia into Maryland, North Carolina, and South Carolina. One unit within the formation that is an area of interest is the Sunken Meadow Formation, or the Sunken Meadow unit. People think that this could be the source of radon, but we're not quite sure if it was the Yorktown or Eastover that underlies the Yorktown Formation. So for my sediment cores, I chose 4 different cores that all contained the Yorktown Formation, because this is what we're trying to get out. Is the Yorktown the source of the radon, and what is causing these high radon levels? And so I have 4 sediment cores that I chose kind of a little bit spaced out from Williamsburg so that we can continue expanding our knowledge on radon in the coastal plain. This is a picture from earlier this summer being in the field. I love this picture because there is so much going on in one little frame. In the back right over here, this is our friend Steve. He's a driller. He's been drilling since he was 15 years old, and he learned it from his father, and his son does it too, which I think that's really cool. But yeah, so he's been doing this for many, many years. And as I was learning from him and watching the drill rig work, he was talking about how based on the vibrations and the behavior of the rig, he can tell when you're going through a sand, a clay, or hitting a shelly bed. So it was just really cool to see how much experience these people had in the field. You can also see Rowan in the background and Kayla Cahoon at the front. And we took this trip to Maryland just to look at this core. This wasn't one of my cores that was being drilled. My cores had been drilled in the 2000s, but this was just cool to see how it actually worked. And so right here, this is where the drilling rod is put into the ground, and it's later taken out by drilling assistants. And after this, it is washed with a hose because there's something called drilling fluid that helps the core barrels get into the earth and not cause too much friction. So you have to spray all that off. And there you see Johnny, he is scraping off the outer shell of the core just to prevent any contamination from depths above that rod. You can also see me taking a picture of one of the sediment cores that just came out of the ground. This is important because people looking back on this core, having access to these pictures is really beneficial. So you can see any fossil structures, the color as soon as it came out of the ground. It's really important. This is about a month after we were at that drill site. This is when I started describing sediment cores on my own, which was so scary, but it was really cool to be able to do. So you can tell that the state of these cores are really different. So from core to core, sometimes it's more crumbly, sometimes there's a lot of shell material. But I love this picture on the right because that's the color of a clay in the Busch Gardens core, which I had never seen that before. I've only looked at a few cores, but I just thought it was really cool. On the left is me looking in a little petri dish at some sediment. This was really important because I was looking for percentages of glauconite, phosphate, and shell hash or shell material. This is important because these are speculated sources of radon in the Yorktown Formation. So tracking those percentages was important for me later to run some statistics tests. And also on the right, one of the days that we were at this warehouse in Richmond, our friends Scott and Todd brought a microscope with them, and we looked at some sediment under the microscope just to see what we could find. And we found this little thorium, which is just like a marine microorganism. So it was really cool that after like 20 years that this core was taken, you can still find new things. So yeah. You might be wondering how I knew where in the cores to sample my sediment. This is a handy dandy geophysical log, specifically a gamma log. So on this left vertical axis, you can see here depth starting at the surface and down to about 120 feet. This line here shows where there's peaks in radioactivity. So like this is a peak, this is a peak, these are some peaks here. And these are really helpful because it indicated to me where I should sample my sediment. And so right around here, around 30 feet in this core is where the Yorktown Formation was. So I knew that there was some sort of radioactivity in the Yorktown Formation. However, with a geophysical log, radioactivity spikes can be peaked by uranium, thorium, or potassium. So I wasn't sure if it was the uranium, which would eventually decay into radon, that was causing this peak. And that's why gamma ray spectrometry is important. So this is a picture of some of my samples from the Bayville core. I put them in these little plastic Petri dishes and packed my sediment in, and then we taped them with electrical tape and later dipped them in wax several times. And this is to literally trap that radon gas in before running them on the gamma detectors. And these samples run for about a day each, so this took a while to get through all of my samples. So while I was waiting for them to run, I was busy making Strater logs. So Strater is a really cool software where you can compile a ton of different types of data into one graph. So as I'm sampling and describing, I had all of this written down that I could add into my Strater logs. So I thought I would just go through. You can see here that the Yorktown contact was marked at about 157 feet, and there's these two gamma spikes here. And so the description at the spike closest to the contact was that it was a fine sand with glauconite and phosphate and lots of shell material. And I thought we could just go through each of these Strater logs and compare characteristics. So the Newport News 2 Strater log at the gamma spike had a sandy clay silt. It was micaceous with glauconite and also had shell material. At the Busch Gardens log, or the Busch Gardens core, we also had a silty sanded shell with fine to medium grain sand, glauconite, and shell material. So there's kind of a pattern we're seeing. This one was a bit different. At the gamma spike, the description was that it was a sugar sand, which just really means a fine grained, well sorted sand with some trace heavies. And so I noticed that there was a bit of an overlap in descriptions where gamma spiked. 3 out of the 4 core logs had a fine grained sand as the major lithology at a gamma spike. There was shell hash, pectins, and oysters in 3 out of the 4 descriptions of a gamma spike, and glauconite at least 5% of the cores. So this doesn't mean anything quite yet. It's not correlation, causation, but it just helps guide us where we should be looking more closely. So with this, I'm going to be looking at these under a microscope to see if there's anything that I can call or pay attention to more closely to see if it's glauconite that's causing these high radon levels, or is it a specific shell? So that will help us further down the road. And I do have results just for one core up here. This was results after running it on the gamma ray spectrometry detectors. And so the Banbury cross core on the left, you can see that I have radium in depth, and on the right, it's comparing uranium in depth. And this one line right here at about 50 becquerels per kilogram shows that there's the average superficial concentration of radium in the Earth's crust is around 50. This sample is from the Yorktown Formation. So you can see that this is extremely radioactive compared to other samples that I took in the core. And so this is just proof that it's uranium that's causing the gamma spikes and not potassium or thorium, which that's important to us because uranium decays to radon. So we know that it is the Yorktown Formation that is radioactive, and we know that there's radon there, and we still just have to get out what's causing the radon specifically. With that, I would just like to thank Kelvin, Rowan, and Jim, my advisors, Kayla for teaching me so much over the summer, and for Scott and Todd for all your help. So thank you.
Questions? Show you chat. Sure.
Nyla.
Is there possibly more that could be done with the information you found in like correlating this of like the radon? Is there more that can be done with this?
Oh, for sure. We still haven't found specifically what is causing the high radon, so we don't know if it's like glauconite that is really radioactive, and it's in the Yorktown, that's what's causing the radioactivity. So we don't know specifically what the source is still. Hopefully later this year, I can run some statistics tests to see if like glauconite and uranium are correlated, or if phosphate and uranium are highly correlated. So there's definitely a lot of research that can be done. And this is just like in Williamsburg, you know? So we still don't know what radon looks like in Delaware or somewhere else. So yeah.
Thank you.
Terry.
Great talk. I wonder why, what's with glauconite? Can you remind me why that's so important in that?
Yeah, so
The question.
oh, Terry asks, why is glauconite important? So that's interesting. It's interesting that you say that, because I was at Aroma's a few days ago, and I was able to meet Sebastian Quote, right? He was our last guest speaker, and we talked about how he's taken samples of glauconite at different wells, and that he's run individual glauconite grains on GRS, and those have been extremely radioactive. And so I just also found that it was a common characteristic of a high gamma spike. So I'm not sure if it's glauconite, maybe it just happens to always be there, but there's definitely something about it that's, yeah.
Follow up to that, but like, why glauconite? Like, why is it attracting this much radiation as opposed to another?
I don't know. We don't know. Yeah. Yeah. So no, you're fine. Yeah. But I think that's, yeah. Phosphate. Because phosphate isn't there a lot of uranium or phosphates in uranium?
They have a similar like weight or
Phosphate takes up a lot of uranium. Yeah. Monica.
So when you sealed the sediments in the petri dishes really well, how did you test it? Like, did you have to break them open again? Like, how did you make sure everything was getting tested, all the gases without them escaping?
So the gamma detectors, they're located in the gamma lab in the ISC, but they're, sealed really well in these little dishes. And then we put them on this huge machine, and you have to like slide open the lid, and it's really heavy. And then you put it on this like carbon disc or something, and you close it, and it counts the emissions or the decay. I can't remember. Jim could explain it a lot better, but yeah, it counts like the different radioisotopes that are in there. And then it like tells us how many counts were like happened, which can tell us how radioactive like the sample is.
So it doesn't have to break it open, it can just tell through the dish.
Yeah, it's because it's shooting up rays, gamma rays. Yeah. And so it counts them. And so it doesn't have to be broken open. It just stays sealed in that little container. Rowan?
Yeah. Great talk. So you know me, I love shells, sanded shells. And the patterns that you have is where your gamma peaks are areas where you have a lot of sanded shell, maybe you have some glauconite. But I can tell you, from looking at those pores, and you saw pictures of those pores in your description, you have sanded shell throughout.
Yeah.
It's the focal plane, like we were awash
Right.
in sanded shell. Why do you think you have spikes in the Yorktown and not the Eastover, which is also full of sanded shell?
That's a great question. Well, I know that a lot of shells that are in the Yorktown aren't in the Eastover, but I know there is a lot of crossover. I don't know. I'm not sure. So something about the Yorktown is different, and I don't know what it is yet. So yeah. Yeah. Linda.
Hi, so I know other students and people in this room have done research on the whale bone
Mhm.
that has uranium in it and radon. And I'm wondering, did you see any
any of that in your layers as particles or anything in what you were describing?
Nothing.
You saw
And I
that?
was on the lookout for it because a lot of my like publications that I had been reading before said that, and Rowan had said that, and Jim had said that. And so I definitely was thinking about it as I'm going through and describing, but I didn't see any bone at all.
And one more follow-up.
Yeah.
Where you're seeing that, is that near a contact? Where you're seeing the spike?
Yeah, there's spikes all throughout the core,
All throughout it.
but like there are very few big spikes, and there's a really big spike, typically around like 30 to 90 feet, which is generally where the Yorktown falls.
Okay, but
Depending
is it at a contact with another formation? Is there, I'm just trying, or is it a member division?
Sometimes it's like right on the Yorktown Eastover contact. Sometimes it's way up into the Yorktown. Sometimes it's at the top of the Eastover, but you also got to think about, we place those contacts. So things might have been reworked and we don't actually know if Yorktown is Yorktown, you know?
Got it.
Yeah.
Thank you.
Vera.
Okay, so the Yorktown Formation, like, all over here, basically. And I'd assume that like the radon emissions aren't perfectly even though like it's all Yorktown. So how would you, are there like any danger signs you could look at and be like, okay, it's like particularly high here, even though they're like under okay.
Yeah. So Vera asked, is there like a sign you can look for that might indicate like higher concentrations of radon in one spot than another? And dangerous, like to us as humans, if you have a basement, you're more at risk because since your house is in the ground, it might be reaching or touching the Yorktown Formation. If you don't have a basement, generally, I don't think you need to worry as much. And like, you have to be exposed to this for like years and years for it to really take effect. So it's like, if you're walking around and there's, you know, something on the ground that's like a whalebone, you know, like you're not gonna get radon or radiation poisoning from that. So, yeah. Anything else? Scott.
In your sample description, I'll ask you a couple of questions. What in hand sample, usually what color is phosphate?
Black.
It's black. In hand sample,
Mhm.
what color is it?
In hand sample?
Usually
Black.
black.
Yeah.
Okay. So what did you do in whatever sample that you know? So you picked out all the black grain,
Mhm.
maybe, okay? What did you do to determine which amount is phosphate and which amount is black?
Glauconite. Yeah, so something I learned this summer is that glauconite can be brown, black, or green, which makes descriptions and percentages kind of difficult. But I learned something from a geologist on the drill site, Pete McLaughlin, I think actually. So he put the sample, just like a little bit of the sample, in like a glass dish and sprayed a little water on it and like kind of smushed it down with his finger. And if there was a lot of green stuff, like the water was really cloudy and green, I knew that there was a lot of glauconite in there. And phosphate grains aren't going to crush like that. So that's how I was able to decipher.
So in your samples then, did you pick out individual grain? What did you do to get this, to give a percentage?
Yeah.
Glauconite versus phosphate.
Yeah. So I didn't pick anything out by hand. That's actually something we're hoping to do. We're hoping to run just like a bunch of glauconite and just phosphate on the detectors.
Okay.
But in order to get percentages, because you might be thinking like, how do you know that there's 7% phosphate? I had a handy dandy percentage book. And so it shows you about how much is 7%.
So that's the total percentage of that.
Right. Yes.
Okay. So now, at some point, wouldn't you want to actually go grain by grain and know that the 7% that you have in your sample,
Uh-huh.
that 1% is phosphate and 6% glauconite?
Yeah, that would definitely be beneficial, but I did not do that. Yeah. So I think I had a lot of other tasks for the match strap program. So I haven't been able to individually pick greens
It's something
yet,
that can be done, sure.
definitely.
Absolutely. I was about to ask that question, what kind of future work needs to be done, that could be done that others would be interested in following up on?
Yeah, we were actually talking about this the other day, just expanding our radon knowledge, just like outside of Virginia, because we've done work in Virginia, but other geologic surveys haven't really done as much. And so we were meeting with Kathleen Farrell at the North Carolina Geologic Survey, and people can do this like same project in other areas. And still like in Virginia, we've only covered a really small amount of ground. So just looking at different locations and doing the same thing I did,
We
basically.
need a drill rig though.
Yeah,
We need a drill rig and people that can.
or you can use existing core too. So, yeah,
Thank you, Allison.
thank you.